Okay, so the first practical activities is about using Cloud Compare, and I mean the point here is that we had to choose software that you could find online, you can find online, and it's open source software. It's software that you can basically also have after the school, because we could have used some commercial software, but that will not have been so good for you, right? So probably we are a little bit more limited in the kind of operation we can do, but this is mostly to give you an idea of the processing of the kind of data sets, etc. you might be dealing with. So the first data set we are going to use is a photogrammetric data set, so something that was built by Ricardo. So I would like to ask Ricardo to introduce this data set, and then we will jump into Cloud Compare if you've got it installed already. Good. If not, you might be able to do so in next 10 minutes. Just do it really fast. So Ricardo, could you tell us something about the data?
Yes. You should see me now. Yeah. Okay. So this first data, I must briefly explain where they come from. Okay. So I can try to share my screen. Hopefully now this time works.
Ricardo, please come back. We lost you, Ricardo. If you can, now here you are. Thank you.
No, sorry, I had a problem with my computer.
That's fine. It was fine. I mean, we were able to see your screen.
Now? Yeah, okay.
No,
No,
at the
actually,
end, but not now.
You are not? Okay.
No.
Give me a second, and I can try to see my PowerPoint, right?
Oh, wait. Okay, that's great. We can see that.
Okay, so just before diving into the dataset we are going to deal with, I would like to start with these two simple images. And if you didn't know where they were took from, I guess that none of you will be able to tell the difference. Okay, so these are two very beautiful outcrops. This was taken on Earth in the Blatterbuck riverbed. You see a very beautiful boulder with cross stratification. Here, a similar formation on the Maury Formation on Mars, imaged by the Mastcam from the Curiosity rover. So this time, as a first exercise, in fact, we are dealing with an analog site. And what is an analog site? An analog site is a place or a condition on Earth that presents analogy with what we expect to find on planetary bodies. It can respect or adhere to different conditions. It can present geological analogies or just geomorphological analysis, or it can present environmental, analog conditions, geochemical, biological, or exploration conditions, like, for example, to human navigation to that specific site. And these sites on Earth are particularly useful, and they were starting to identify them since the Apollo training for the lunar missions, in order to be able, of course, to navigate and perform tests. So the best way to prepare for space exploration is, of course, test in real environments that we know are have the most possible similarities to what we will observe on the planetary body. And of course, also this applies to science, because we have our test bed just here on Earth, identifying the most suitable place. We can then, by comparative planetology, infer some similar conditions or processes affecting similar landscapes or geology on another planet. So specifically referring to the picture I've shown you before, this was taken into the Blätterbach Gorge, which is a UNESCO World Heritage Site in Alto Adige, near Bolzano in northern Italy. And this place is particularly spectacular because it's on the side of a mountain, which is carved by this river, called it's the Blätterbach River, and it exposes completely the sequence from the Permian to the Triassic of the Dolomite. So basically, this river carved on the whole mountain, and you have all the stratigraphic succession exposed. This is an aerial view where you see that from the top you have this gorge developing with the river, and these outcrops were photographed just here below. Just to give some more context of what you see from the top of the mountain, this is the gorge with the river, and here all the stratigraphy happening. These are some dolostone, there are Mars, there are sandstones, and so on. We will have a look at here later on with our outcrop model. So how this place formed, very briefly, in order to analogy with Mars. So this place was developed on a crystalline basement and on some volcanites, it's like porphyrites, in a sort of a tidal plain with aggression of the sea inside the land, with the formation of paleo channels and of an alluvial plain. So we have the basement is composed by volcanic rocks that were eroded, disrupted, and reworked by the tidal effect and also the effect of the rivers. This is the stratigraphic succession. So at the base we have volcanic rocks from Mars that are degraded and eroded by fluvial activity or water activity, and reworked and redeposited like on Mars. And so we have a pack of sandstones with different granulometry piled up on top of these volcanic rocks. And then we have a deformation of all the carbonates and so on that we will find on the Dolomites. But the important section is this one, which has the similar conditions, both in terms of paleo-environmental conditions, but also morphological conditions. So going back to the gorge inside, from let's say the ground truth perspective, we might say that we have the rover perspective here. This is how it appears. So we are working, people are working actually on the porphyrites, on the volcanites. And on top of that, we have this formation of sandstone that you see are more or less lithified as rocks, but they are also very heavily eroded by the weather. And this is, by the way, astronauts training with the Pangea is training inside this place, and we'll talk about it later. Another example of similarities you can find in the Blätterbach Canyon is not just the cross lamination, but also the mud cracks. This is a negative footprint of mud cracks. This is my foot. And this is the same on Mars in the old soccer rock imaged by the Curiosity rover. And inside here, you see something very nice. So we have the negative of the cracks of the mound here and here, but also here we have this white veining all around, this boxwork of white veining. If we look at the walls of the canyon, we can find this veining all around inside this reddish sandstone that have the same composition of the volcanic rocks just lying below. These are just eroded and reworked. And then there is some activity, some possible past fluid activity that are creating these white veins that are actually similar to the Garden City outcrop, for example, in the Gale crater again. We will have later things, but the similarities with your, let's say, very briefly. This is just a close-up image, another close-up image of the site. And this is Nicolas Mangold, scientist of the ChemCam team of Curiosity, training Samantha Cristoforetti, the astronaut, about this planetary analog, so showing sandstones and this veining of gypsum that is cross-cutting the whole formation. So this is a perfect analog for Mars with respect to paleo-environmental conditions. So a good way to work on an outcrop like that is that we have much more control on the information we can gather on its 3D shape. Of course, we have the rover on Mars that takes pictures, okay, but the ability to move is quite limited in a way. Of course, this is the best we can get, but of course, when we are on the place, we can have our reflex camera, our drone. We can take several pictures of these outcrops like this one, and we can then obtain a very good model by putting together all these pictures with all the locations. You see, these are the thumbnails of my cameras. These are the positions, and Gwenelle will speak later on again in this morning about how this process works practically. But ideally, this can be taken all around the outcrop. They can be joined together in a point cloud. So these are the points that are identified within several pictures and created into the 3D space. We can create a dense point cloud, and then we can mesh the point cloud and apply a texture that is a mosaic of all these pictures deformed together and stitched to the 3D model like this. And we will get a beautiful 3D model of this outcrop with all the gypsum veining, and we can try to derive geological information from that. We will have the same on Mars, but of course, the best place where to test our methods is on Earth, because we have control on how we take pictures and we can get better details. This is very, very brief introduction on the activity of today.
Okay, thank you, Ricardo. So we can jump in using Cloud Compare. If any of you, could somebody tell me if they will try to replicate that, to replicate everything? Just to know, because if all of you are just watching, we can go faster, or if you would like to do it now, it's totally fine. No, nobody wants to tell me.
Oh, I would like to try.
Okay,
yeah, there are a few
great.
people in the chat.
That's great. Great,
Yes,
thank you.
me
Thank
too.
you very much. Okay, so I will share my screen. Let me find Zoom again. Share screen. Okay, so basically this is the main interface of Cloud Compare, right? You can open it up if you have got the software installed. If any of you have troubles, let us know. But of course, you can open it like any other software you've got on your computer. So let's have a look at the data we provided you. We have two folders. The first one is the...
Just a question.
Yes.
This is not the QGIS, so should I install some of the programs?
Yes, of course. I mean, you can just follow with us and then try to install it later. Have a look at the software page on the website. We listed the software that will be needed to actually follow in real time. But I repeat, it's not really so important. The important thing is that you see, have a look, and then you can later take your time to play with the data. That I believe is the most important thing now.
Thank you so much. Okay.
Okay, so let's see the data in the Blätterbrack analog. So when you are working with 3D data, please pay a little bit of attention, because I mean, it's very easy to let's say load 10 gigabytes of data in memory and you don't have the memory on, maybe you don't have the memory on that computer. So we have prepared two different resolution of the point clouds. One is the high res, one is the low res. You can try to open both. But if you find yourself in trouble with the low res, just don't try to do the high res, because it might lock your computer down for several minutes, or you will need to restart. So I will just use the low resolution one. And if you drag and drop your file, it will be directly loaded by Cloud Compare. So again, we have two different resolutions. One is the high resolution, another one is the low resolution. You can choose which one you want to use. I suggest you to use the low res one, it's more than enough, and then later you can play on with a higher resolution dataset. So if we are on the same page, I will just introduce the interface. So basically you have a central window in the middle of everything. That is the three-dimensional space. Here in the bottom right, you can see the axis. So if you move around, you have a reference. The red one, I guess, is X, Y, Z. That should be the green one. And this is a scale, right? So it gives you an idea about the scale of what you are looking at. And just by using your left click on your mouse, you can move objects around. So let's as a first thing try to understand what we are looking at. So try to navigate your data set, to orient it so that you believe it makes sense for what we are looking at. You can zoom in by using the wheel, the little wheel in the middle of the two buttons of your mouse. If you use the right click on your mouse, just try it out. You can just move around your model. That's pretty slow on Zoom, but of course, that's why it's better if you do it on your computer. Okay, so basically in the interface, you have this dialog that can be docked anywhere on the software, so might be not exactly at right, depending where you decided to put it. Let me try to dock it again. Here it is. And basically, it will list all the entities which are loaded into the scene. You can disable some entities and then enable them again. Of course, even if you disable an entity, it will be still loaded into your memory. So that will account for the whole memory you can use for such task. The object can be organized in groups. So like in this case, you have this parent folder called Blätterbach, low res, etc. And you have just one child that is a point cloud. You see from the symbol, there is a little cloud, and that is the Blätterbach high resolution point cloud. You can, of course, add new empty folders to organize your data. You can move your data into different folders. When you select some 3D data, you see that this bounding box, these yellow lines light up, so you know which features you are selecting. If you deselect, it disappears, and so on. When some features are selected, you will also see in this other docking window called properties, all the properties of that object. So you can change several properties, of course, visibility, but it basically just make it disappear. Most importantly, you can set which data we are using to as colors on the point cloud. So now it's set to be RGB. So we are basically using the RGB colors from the pictures. You can change it to scalar fields. Okay, this is what we were talking about before. A very important thing is that we can associate values, right? Values and vectors to the data, because just having the data is not totally the most useful thing, because you can just visualize them. But if you can merge that information with other sources, and you can associate other information, that is the real power of using 3D data. Of course, you can change which scalar field to use to visualize the colors. And in this case, we have several. So you see three scalar fields, which are just the components of the normals. So the X, Y, and Z component of the normals. We have several other scalar fields here, which are just the output of the software Ricardo showed you before. So the software creates the model in this way, and also associate some additional information you can use. So for example, I don't know, confidence is very likely to be a measure on how much the model is good in that location. If you scroll down always in the property, you can find some other controls like this scalar field display parameters control, and where you can customize the range of the scalar field that is used to visualize. So you have those little, let's say, circles. You can drag and you can drag them, and you see as you drag them, the color representation will change depending on the threshold you put. So it might be good also to experiment with different thresholds depending on what we are doing. And probably if we have time, we see an application of that later. So here at the bottom, you can see something that is called transformation history. And this is very, very important because anytime you apply a transformation matrix to your data, so what we were telling you before, so it's a 4x4 matrix because it is expressed in homogeneous coordinates. And it both contain the rotation that will be this matrix, this 3x3 matrix, which also might contain skew and scale and other linear transformation, of course. And those three values here correspond to the translation of your object in space. So let's see an example. Let's see how we move objects around, really not just for displaying, but if we need to move in a different location out to the model, you can use this tool here in the toolbar that is called Translate Rotate. Of course, you can find the same tools by looking around in your menu. And for example, you can find Translate Rotate also there. So for example, if I press Translate Rotate, I got this little dialog opening, and you can choose whether to rotate around a specific axis or do not rotate anything or just apply translation. So let's see what happens if I use my right mouse click to move it. Okay, let's say I moved it, and now I will just press this little flag here, so to say accept. So we are happy with the rotation, with the translation. So let's see what happened to our matrix. And here we are. So as we explained before, in this matrix is contained all the information needed to locate your data in the 3D space. And this will contain all the transformation history of your data set. So if you start modifying it, changing position easily, you can always come back to the original position by using this metric. So in this example, we had just a translation here. So we moved of 32 centimeter to the on the x-axis, 4 meters on the y-axis, and so on. So for example, if I want to just, let's say, go back at the previous state, you can find here there is no go back function. But of course, what you can do is just copy this matrix, go under apply transformation, that is also Control T if you want to be really fast on that. So you select the cloud, you look in edit, and you find apply transformation. And you see here, you can actually input the transformation you are willing to apply to your cloud. You can use different ways to do that. So for example, you can say which rotation axis to use. So an axis like this would be the Z axis, no? An axis parallel to the Z. And you can say how much you want to rotate your cloud. So let's say I want to rotate around Z of 90 degrees. or I want to apply a translation. And also there are other standards you can use, like Euler angles, or just the three angles in space to rotate by. But the important point here is that I can copy paste the transformation history I got in that dialog, and now I can say apply inverse transformation. So what it will be doing, it will be basically inverting this matrix and applying it again to the points. If I press OK, of course, you cannot see much now, but basically the point cloud came back in its original state, and we should probably have 0, 0, 0 again here. Is anybody able to follow me, or I'm going too fast? Probably I'm going too fast.
I can follow.
Yes.
Great, that's great.
Yes.
Okay, so that's really nice. That's really nice.
Lucas, somebody is asking if you go a bit slower. Just a bit.
Okay, I will try. I will try, but I'm sorry because we know we are a little late and we don't know we will be able to do all the practicals, but that's okay. I will try. So, okay, this is just to introduce you to Cloud Compare. There are a lot of functions. So if you go under Edit, if you go under Tools, there are many different functions. Just one I would like to show you is for cutting your or segmenting out your data, and it's called segment, and has this little icon of the scissors. You can use it. You can just select your point cloud, and then, for example, select a little subset of your point cloud like this one. Then there are several tools here. The one I will be using is this one. You can explore what the others do. You can find a lot of documentation also online. I will use this segmenting and then apply, right? With conform selection, or just enter. I will just conform my selection. Let's see what happened. So starting from the original point cloud, we cut out a little piece, and we have that little piece separated, right? So if, for example, we want to analyze this data in detail, it might be good to just crop out a little bit of your point cloud or your mesh to just work on that.
Luca, I have a question.
Yes.
Would it be possible to crop that area of the high res without loading everything of the high res data? For example, I don't have enough memory to...
No, not actually, but there are probably ways to do that, but not with Cloud Compare.
So maybe what I had in mind was if you load the low res, which should be the same image that we have in high res that you provided, if we maybe have the location already placed on the low res and having it extracted in the high res, maybe that would be a possibility.
Yes, but it's not something that is super easy to do here. What I've been doing in the past for situations like this is, like you said, using a low res model. So for example, I would use this function here that I was going to show you anyway. So it's called trace polyline by point picking, right? And you can trace polylines. So for example, on this point cloud, I decide that, for example, my polyline is something like this. I don't really need to precisely close, but better it is. So when you use this function, you will create a new polyline, right? And it's not exactly like doing a selection, but what I've been doing in situations like this, for example, when I needed to extract hundreds of small locations because I wanted to estimate some parameters for that location or stuff like that, I used a set of polylines. So I was basically tracing each polyline where I wanted my analysis to be made. then, for example, if you save this polyline, you will see that, for example, in a text file, you can very easily save it. And if you go and have a look on what is inside the polyline, is let me find it. Polyline, that one. That's perfectly good. If you open it, you will find that you have just the list of the point, right, of that polyline. So it's not that it's a perfect solution, but what I've been doing, I was post-processing this information to extract the IRS data using that kind of polyline. It might take some work, but it's not totally impossible. So you basically have to load your data in, I don't know, MATLAB, Python, whatever you want, process the polyline information to get the best fitting plane, and then you have to project all your data points on that plane and see whether they fall within or outside the polyline. There are tests to do that.
Yes.
But it's not something that is, I could say how to do that within Cloud Compare. So in the past, I developed a plugin for Cloud Compare that was making exactly that. So you would have been using polylines and then create small volumes, bounding boxes that you could use to extract information automatically from point clouds, for larger point clouds, for example. But the plugin is not maintained anymore, so I don't have much, because I don't have much time, but could be something like that might solve it.
Okay.
Okay. So you already have seen how to trace polyline. So that might be important whenever you are trying to do a geological interpretation. Let's go back with RGB. So for example, you can move around, and for example, you want to annotate something, a linear feature, so you enable the polyline tool, and you can, of course, trace whatever feature you like for example, this little fracture filled in with gypsum. Is that gypsum, Ricardo?
Yes, it is.
Yeah, great. Okay, so you can actually collect some information from an outcrop like this by using those techniques. Then, of course, we will see later how to use that information to create something like stereo plots. We will try to see whether the ones of you which are not geologists, you can give a brief explanation of that, and we will see how to do that. So I would like to go ahead with the Cloud Compare demonstration. Let me find out where we are in the schedule. Okay, I'd love to ask Barbara now to give us a brief introduction of the site that we will be using for the Mars case. If that is right, Barbara, are you here?
Yep.
That's great.
Okay,
because I just wanted to say we're going to use a different data set. This one was made of point clouds, just for you to have a feeling of the software and working with point clouds. Then we will see the difference with a mesh, and we will see how to work out with that. But I need Barbara to give you a little bit of scientific context so you can better appreciate what we are going to do.
Hello, everybody. I will just give you a little bit of context, the scientific context about the case study that you're going to see for Gate Crater. The process of analyzing is mostly the same. It's just to let you see how we can use 3D modeling to extract information from planetary surfaces. I should be able to share my screen. Can you let me share my screen, please?
No.
Okay, you can do it now.
Great, thank you, Matteo.
Okay. Okay. Do you see my presentation now?
Yes.
Okay.
Yes.
Okay, great. As I was saying, let's go and see how we can use these tools to analyze something that's beyond Earth. Okay, so you've just observed the case study on Blatterbach on Earth. Now we're going to walk on Mars. We were, at the time, our aim was to look for fractures that acted as conduit for fluid flow, so something similar that you was just seeing, the veins filled with minerals. And that's exactly what we went to analyze on Mars. And we decided at the time to use the Curiosity rover data that was probing and is still probing Gale crater that's located here. And this is the part of the crater where the rover is probing. So let me give you a little bit of context. So of course, as I said, Curiosity rover, when we started the study, was already there. We already knew there were these kind of veins similar to the ones you see in the Blatterbach case. But I want to let you know why Gale crater is so interesting, and this will be useful to understand the final conclusion and interpretation that we will be able to extract thanks to the cloud compare analysis in the very end. So as you see in the slide before, Gale crater is located at the lowland-highland dichotomy boundary on Mars. That's the place where we can find a high density of water-related features, which are very interesting concerning the Martian parts that we are still studying. There's still a lot of questions about, and this is an area where we can have a lot of these kind of features. So this, first of all, is a very interesting point. Then we also know that Gale crater rings, so the impact that generated Gale crater are 3.5 gigayears old, meaning that around that time the impact happened. The reef was there before, and then the crater, let's say, started recording what happened next, which again is a very interesting period in the Martian history. In fact, 3.5 gigayears ago on Mars, we were at the Noachian-Hesperian transition boundary. That is when we presume that the climate optimum that was present on Mars started to decline. In fact, before that moment, we know that for a prolonged amount of time or for just short amount of time, but anyway, there were the condition of temperature pressure at the surface to have liquid water carving features on the surface, building new features on the surface. And after that moment, that situation started to change from this water stable at the surface to what we know today. This is to say a cold and dry Mars. So again, Gale crater recorded a very interesting period of the Martian history. On top of that, we know that such rings are cut by fluvia channels, as you can see highlighted in red in the slide. And at the end of such channels, we can see that there are 3 delta funds that are filling Gale crater on top of the flattish surface that's below, which also is a crater infilling. And 3 delta fans are a lot for one crater. So overall, Gale crater is extremely interesting from the environmental reconstruction of Mars and whatever studies you intend to do concerned to water presence and circulation there. So that's also why we decided to study this kind of place on Mars. So let's get a little bit into detail. As I was saying, Curiosity rover were already probing Gale crater when we started the study. In fact, he landed around 2012 in this portion here of the crater and started his journey. Gale crater, you can see it here on the left, is a very complex science laboratory, but we were particularly interested in its eyes. In fact, we use MASCAM images, which is a camera that's acquiring true RGB colors, meaning that MASCAM observe on Mars almost what the human eyes would perceive there. And that's exactly what we needed, because we needed to see such fractures and how they were distributed in space. Then here you can see the traverse that Curiosity rover traveled along, and that's where the rover arrived this summer. So I guess now it's way beyond this point, but nevertheless, we were interested in the portion of Mars surface that the rover acquired here in the red circle that I highlighted in the image. So let me give you a little bit of context on that area. So that specific spot is located on the Murray Formation, which is composed predominantly by laminated mudstones and is at the very base of Mount Chop Group. That here you do have the stratigraphic column, and here you can also see the geological contact between the Bradbury group, that's the older one, and the Mount Sharp group that's here, that's the new one. And we are at just the base of the Mount Sharp group that Curiosity rover crossed the boundary just approximately here and started moving to younger formations. Along its traverse, Curiosity observed enhanced chemical alteration, widespread post-depositional history, meaning that water had a very important role basically during all the phases of the generation and post-depositional history of such formation that we're gonna study. So why we decided to analyze specifically that spot? So as you can see from the animation of the slide that I hope you are able to see, in this particular area, there are these knobs that are outcropping from the sand. And on these knobs, as you can glimpse here, there are some fractures that are filled with whitish materials, which can be followed all around the knobs. And this was very important because most of the time that Curiosity observed such veins along its traverse, we were in this kind of scenario. Most of such veins were on floors or outcrop that were visible just on one side from the Curiosity perspective. And so this is a very good information because you can effectively see the vein, you can see that's filled with whitish mineral, meaning that at a certain point some fluid probably flew around that, flowed around that, and that's good, but that's not enough for what we wanted. We wanted to perform a structure analysis and understand which kind of history these rocks went through. And so that's exactly why in this case differently, which is this second case scenario, we were very happy to have the opportunity to do this kind of study, because when you do have the three-dimensional information, you can place plane in space and do a structure analysis, a consistent one. So to do that, of course, we use Cloud Compare. And at this point, just let me point out just one difference between Earth data and planetary surfaces, which has been already introduced by Ricardo. Let's say that when we went to Blätterbach to acquire such the data that you were handling, we went there, so we were there in person. We were able to observe the outcrops ourselves, and we decided which outcrop were the best for our study, and decided for the illumination situation that we were dealing with, and then we acquired the information, more than one if necessary. So the amount of data, the amount of information we had were enormously bigger than what we can usually have on planetary surfaces. In fact, in this case, we had just that Curiosity were passing by and looking left and right and recording what was surrounding the probe. In fact, for that, we have a dishomogeneous point cloud, pretty much dishomogeneous. Here, I try to highlight in green the points that were more, where the point cloud was denser, and in blue, the point cloud was less dense. And as you can see, the denser surfaces were the ones that were favorably oriented, meaning the ones that were perpendicular to the line of sight of Moscom. Differently, some other surfaces were not favorably oriented, like the ones that were parallel to the line of sight of the camera, or where the knobs started to bend and were bend beyond the line of sight of Curiosity. And that's something that you need to keep in mind when you will be dealing with those data, or when you will be dealing with the data that you need for your work, because sometimes you just cannot extract the data, and that's in a certain way good, because you know that you can't. In other situation, you will be able to extract something, but you need to pay attention, because sometimes that something might be wrong, and you need to be aware of that. So in our cases, we were anyway able to extract enough information to perform the analysis. Here we are zooming in our area, and you can see we can start glimpse the fractures. And what we did was something similar to what Luca was showing you before. So we traced polylines where we saw the fractures outcropping on the knobs, and we extracted from such polylines the planes that corresponded to the three-dimensional information of what we were just seeing running around the knobs, let's say. And that was possible through Cloud Compare Compass plugin. In the very end, the results of what we were doing looked like something like that. So we had all the knobs cut through these planes, but yet by itself, it's very hard to give a quantitative information just by having this kind of representation. We needed something that could be easily visualized, also because these are just part of the knobs, and it was very hard to have a glimpse of everything just with one visualization. We needed to move around our mesh. So we decided to plot everything on a stereo plot, which looks like that. This means that basically we put all the planes we were able to map together and plotted them on a sphere. I think you will say exactly in more detail how to build one afterward. And basically, you do have a sphere where you see the lines correspond where the planes are cutting such sphere. And so you can see here that we were able, thanks to this kind of visualization, which brings everything together, to distinguish 3 different families of fractures. The first one that's possibly the most intuitive one is the one represented by the greenish planes, which were horizontal planes of fractures. And then there were 2 other families of fracture, which are represented by the red and the blue one, which were dipping 60 degrees respectively, but in opposite direction. Thanks to this information, we could move on with structure analysis. And this was very important to have this quantitative information and just a qualitative glimpse of what was there. So let's start to using this red and blue family of vein to reconstruct what happened in Gale crater. So we know, thanks to studies of Earth, how rock crack when they're under pressure. And we know that when we do have these 60 degrees apart kind of fractures, it means that the main pressure, the most energetic pressure, was coming from this axis with the respect of the geometry of such veins. In our cases, you can see some of these families of fractures here and also here. I hope you can see my cursor on the landscape. So in our case, this main pressure, the main stress were coming from a vertical axis, meaning that something was pushing down our rocks and up to the point of cracking them. At this point, we were very happy because we were able to retrieve which kind of stress situation we had that led rock to crack and to degeneration in somewhere of those fractures. But as you can see here, there's no set of horizontal planes that you saw before. That is the third one of the families of vein that we were able to map thanks to this analysis. So very happy to know that that was the stress distribution. Anyway, what we just observed did not imply in any possible way the presence of fluid, which was exactly what we were looking for here. We were interested in fluid circulation in the very end. So we wrapped our mind around it and realized that to have also the production of such horizontal set of veins, we needed to have fluid circulation through such veins to have that stress, having this stress distribution. What does that mean? So we have this pressure pressuring our rocks from above and cracking them in this oblique sets of veins. And at the same time, we also have to consider that we had fluids flowing through them. So let's move to the sketches here. And when such veins cross-cut some weakness surfaces, fluids are very likely to use those weakness surfaces and start propagating new cracks. Here in the Earth image and the sketch, the weakness surfaces are nodules. In our area, we did not see nodules, but if you remember what I said before, we are dealing with laminated mudstones here, and each lamination boundary acted exactly as a weakness surface. So basically those cross-cutting oblique veins cross-cutted a lot of such lamination boundary, and when fluids started to move through those fractures, they used a lot of these laminations to open new horizontal fractures. And this phenomenon is called hydrofracturing. So at this point, we were very happy because thanks to this quantitative information, we were able to understand the stress condition that cracked the rock, and also that fluids were needed basically to have this scenario happening. So overall, let's wrap everything up together. We were able to reconstruct, thanks to this information, the geological history of Gale crater. And we knew that at the very beginning, Gale crater was probably a lake. mud accumulated, compacted, and consolidated, generating the mudstone we are observing today. And in a second moment, some new pulse of material deposited, overloading the underlying material. That we have to remember there was mudstones, but also some fluids were accumulated in such mudstones. And so overloading them, we were also pressurizing such fluids. At a certain point, pore pressure exceeded the rock strength and cracking and faulting started. Fluids, so we started generating such oblique families of veins, fluids start flowing through them as preferential pathway to be squeezed some from somewhere in subsurface toward the surface. And along their way, they started fracturing also the horizontal family of blades. So this is basically a quick glimpse of what can be achieved with these tools. And of course, this is very geologically oriented. And also this is the case study that you're going to see during the second part of the practical. I hope everything was pretty much clear. I'm taking question if we have time, and otherwise I leave the stage to Gwenal, I guess.
Yeah, that was great, Barbara. That was really interesting because we see the whole process. So it's not just to start from cool 3D models just because we love them, but also using them for doing science. So it's just great. So I've asked also Gwenal, if he's here, to give a brief presentation. He's a master on photogrammetry reconstruction, so I'm pretty sure if he's with us.
Good morning, everyone. I am here.
Oh,
yes.
Here it is. Hi, Gwenal.
Hi,
Thank
Luca.
you for coming.
No problem.
Thank you
My
very
pleasure.
much. Okay, just a little thing to say. I know you are expecting to do practicals. We are going to do, but of course, what I believe is more important now because is to get the context in which those kind of practicals are made, rather than knowing how to use the software, because you have a lot of documentation online on how to use the software. Just Google it, but putting all the pieces together, I believe it's more important now. So Gwenal, if you could introduce us how you have been working with this kind of 3D data, that would be great.
Yes, of course. Thank you, Luca. So good morning, everyone. I am Gwenal Caravaca, currently a postdoc in the Laboratoire de Planetologie and Geodynamique in Nantes, in France. And my main work here and for our project is to reconstruct outcrops on Mars, but also on the Moon, using the methods of 3D modeling that Ricardo, Luca, Barbara just talked to you about. So for today, maybe it will be a little repetition of something you just saw minutes ago, but I wanted to enter in more details into what it is really to make a digital outcrop modeling. So to give you the little technical insights onto the background of this technique. So this will be a very quick introduction on the method, and I invite you to stay tuned and connected this afternoon for the follow-up with my colleague Stefan. So first of all, what is again a digital outcrop model? So a digital outcrop model, or DOM, is before everything a 3D, realistic and accurate recreation of an actual geological terrain. So that is, it can be on Earth, Mars, Luna, or beyond. And what is important to understand is that a DOM is differing from a DEM, a digital elevation model. So on the right of the slide, you have two photos, one of a DEM, so as you can be used to see in your favorite GIS software. So a DEM, a digital elevation model, reproduce a surface. So that is, we are not in 3D here, but like in 2.5D. A DEM is characterized by the fact that each XY point is only having an only value of Z. That is, here on this grid, for each XY point, I have only one Z value, which is the altitude. So using a DEM, you can reconstruct the relief of a region, but for a given surface. The main difference with a digital outcrop model, a DOM, is that here we are not dealing with a surface, but with a volume. So here, potentially, each couple of XY points can potentially have a multiple value of z of altitude. That is, to be simple, is that on a DEM, you cannot reproduce a vertical plane, such as a wall, but with a DOM, you can reconstruct this vertical plane. And if you are looking here on the right side of my slide to this digital outcrop model, you can see that there are a lot of vertical panel, which is very common in the section modeling. So that is the main difference to understand between the DOM and DEM. So why are you using those digital outcrop model, except for just having a 3D representation? Because the digital outcrop models are very useful in recreating the actual shape and morphology of the geological features. You just saw in Barbara's talk that it was very important for her to be able to see the different planes of the fractures in the 3D space. So that is why it is important to actually reproduce it into a 3D mesh, because we can observe it from any point of view and have a real sense of the volume, and to also avoid any deformation. For example, here on these two images from the Kimberley outcrop in Gale Crater, as seen by the Curiosity rover, you can see here on the left side of the slide a 2D view, and on the right side a 3D view. You can see the main difference is that in the 3D view, you can see flat lines representing the beds, and you cannot see the horizon. On the contrary, on the 2D view, it is interesting because you can see very far on the horizon. But this is the main problem of the 2D view versus the 3D view. On the 2D view, you will have some artifacts and some projection errors due to the parallax, the way the photo is taken. And so that it induces any very important deformation due to the projection. The 3D model, in comparison, will allow you to observe the true shape without those kind of deformation. So that's why it is very important to use a digital outcrop model and to be able to compute them from the data we have from the field or from the robotic probes that we are sending to Mars, the Moon, and beyond. So how to do these digital outcrop models? Ricardo, on his presentation, talked to you about the photogrammetric approach. It is interesting to know that you can do these digital outcrop models by photogrammetry, which is creating a colored or textured mesh, but also using LiDAR detection. I have seen somebody a little earlier asking in the chat if the model explained was a laser scan. Typically, LiDAR detection allows to make colored point clouds that are the laser scan. So here on the upper side, you have a laser scan, which is made by a dense point cloud, each point corresponding to a reflection of the LiDAR scan. And on the bottom, you have here a photogrammetric model that has been reconstructed using 10 or 12 images. And you can see here even the borders of the images because we need to have overlapping image, but I will come to that in a very few minutes. So you have understood that in this presentation, we will focus on the photogrammetry. You have to know that there are two kinds of photogrammetry. The first, the most known method, is the stereophotogrammetry. It is usually used to compute the relief from 2 or 3 ortho images that are overlapping. And typically, this is the method that we are using to create digital elevation model. So stereophotogrammetry is very useful to make DEMs, but not so much to make DOM. And to make DOM, we will use the structure from motion photogrammetry. So you have seen several examples just before on Barbara and Ricardo's presentation, but here I will enter a little more on the detail of how the structure from motion photogrammetry works and how it can be used to recreate the rocks or geological feature model. So first of all, you're taking a very big number of overlapping photos. it is very important that your photos are overlapping and covers a large area of the object you want to recreate in 3 dimensions, because the photogrammetry, the structure for motion photogrammetry relies on algorithm that will compute the place in a space, in a 3D volume, of the different points of the object you are taking in photo. So here you can see my little sample of rock here, this gray rock, has been taken from multiple points of view in photo. And here the software has detected 4 points that has been here represented in, that has been represented in red. So you can see that these points are specified in very different position on the 2 photos. So this is very important to understand, because that is the difference in position of these specific points within 2, 3, 4 or more overlapping photo that will help the software to reconstruct the shape, the 3D shape of the object. So going from these overlapping photos, the software is able to reconstruct a sparse point cloud and then a dense point cloud. So these point clouds are just points projected into a 3D space that will reconstruct the 3D shape, the 3D shape and form of the object into a 3D space. That is, we are transforming a real physical rock into a series of X, Y, Z digital points into a virtual 3D space. Then, when we have these point clouds, we are able, or at least the software is able, to generate a 3D mesh. And what is a 3D mesh? A 3D mesh is a set of polygons. That is, the software is just linking any of these points to make triangles, triangular faces that we are calling polygons. And these polygons, as you can see, is what we recreate the 3D shape into the digital space. So obviously, this structure for motion photogrammetry is fairly quick and easy to do, and I encourage you to try it by yourself. There are multiple solutions and software that are able to do that. Most used are Micmac, Visual SFM, Reality Capture, Metashape, 4D Mappers. There are very a great number of software, and it is the most used method to recreate outcrop models in geosciences, both on Earth and on the planetary bodies in planetary geosciences. So here we have used this very method to reconstruct another outcrop in the Gale crater that has been visited by the Curiosity rover, which is the Kimberley outcrop. So Kimberley outcrop was visited a little earlier than the outcrop described by Barbara earlier. As you can see here, it is a little closer to the Bradbury landing site. And Kimberley is a very interesting outcrop because it features this very nice butte with a series of lithified fluvial sediments. But how to recreate the Kimberley outcrop? We have used for this about 2,000 images. I let you imagine it is a very large quantity of photo. And as Barbara explained earlier, the Curiosity rover is equipped with different cameras. Some of them are in grayscale and others are in colors. Obviously, the color images are the most interesting because we have the highest resolution and we can see a lot of details on these images. But the navigation cameras are in grayscale. However, these navigation cameras are very useful because it is a stereo pair there are two cameras taking the same picture at the same time, and thus we are able to reconstruct the relief. So using about 2,000 images taken by the rover, we have made several steps using a photogrammetry software to reconstruct the Kimberley outcrop. And you can see here the different steps that we have done. And you can see that it is a very long processes to be able to reconstruct an accurate reconstruction, because the main difference between photogrammetry on Earth and photogrammetry on Mars is that on Earth you can take any pictures, as many pictures as you want from any point of view, but on Mars we have to deal with the limited movement provided by the rover. So you can see on this process that the Kimberley outcrop were first reconstructed as a sparse point cloud using only 500 cameras, the navigation cameras. And then we were able to add the nearly 1,200 mass cameras, that is the color imagers, to be able to reconstruct a dense cloud. And you can see that this dense cloud is composed of about 100 million points. That is a very big dense cloud. Another important thing to understand in the photogrammetry process is that you can use it to reconstruct objects as little as a very little pebble, or to reconstruct very big outcrops. And here the Kimberley outcrop is about 2,000 square meters large. It has a very big area. It covers about 50 by 60 meters. And the photogrammetry allows us to deal with such amount of data. So here in this little video animation, you have a view under Cloud Compare software of this outcrop. So you can see it has been reconstructed from with various level of detail, because there again, the photogrammetry is not a perfect solution and it relies on the quality of the photos you have taken. So if I stop the video here, you can see that the outcrop in this area is very finely defined, because as the rover was just here, and it is shown by the tracks here, you can see the tracks left by the rover on the Martian dust. The photos were taken from very close, and then we are able to reconstruct a very finely defined model. But the farther you get from the position of the rover, the more deformation you will have. And you can see this on this area here, on the top left side of the little animation. You can see there are a little error of projection, because this area was a little more far from the rover than the position where the photo were taken. So keep in mind that photogrammetry is a very good solution to recreate outcrop models, but as any of other modeling methods, it has its limits, and you have to keep this in mind when you want to reconstruct a digital outcrop model, that you will be able to reconstruct specific parts that are close from the multiple point of view in a very good fashion, but you will have to limit yourself on those areas that are a little more far. So obviously, the digital outcrop modeling reconstruction is possible whenever and wherever you dispose of a sufficient number of overlapping photos on Earth and beyond. And here I will give you two last examples. On the left, this is a workspace of the lander InSight, which was made using about 60 photos that were the very first photo coming down from Mars when InSight landed 2 years ago. And on the right, you have another Earth-based model, which is a coastal outcrop here in Western France. So you can see the size are differing. For InSight, we have about 3 to 4 meter large area, whereas here on France, we have a coastal outcrop, which is 50 meter large, just because we were able to take a lot more images, because we were able to go there. So if you want to go further about and want to see these digital outcrop models, I invite you to go to the Sketchfab website to check the PlanMap and LPG's account. We have a little library of the different digital outcrop models we are using for the project. But I encourage you also to browse on Sketchfab. There are literally tons and tons of digital outcrop models that are very exciting to see, and that will give you a taste of what a powerful method the photogrammetry is to recreate outcrop models. And finally, as a little spoiler for this afternoon, to go even further in working with digital outcrop modeling, Well, what is better than only seeing and working with the 3D model on the computer? Well, it is to experience it. And the next step in using these outcrop models is the integration within a virtual environment and then seeing it in virtual reality. So to know more about this, I invite you to stay tuned and stay connected to the Winter School channel this afternoon. And then Stefan and I will talk to you during the From DON to Virtual Environment courses about integration of these models in virtual reality. Thank you.
Thank you very much, Gwenel. I guess there are a couple of questions, so we might relay them to you. Let me see. Kai says, is it more helpful to have taken photos from different elevation compared to having the camera always in the same horizontal plane? Indeed, is what you had there, right? The camera always in the same plane.
Yes, exactly. As for Curiosity photos, the photos are taken from the mast, the remote sensing mast, which has a fixed height of 2 meters. So obviously, we have the photo taken from the only horizontal planes. For the coastal outcrop that I have shown in example in France, we had also a fixed height on the camera tripod. But if you have the ability and the possibility to take additional photo from different altitude, for example, using an UAV, it is better because in photogrammetry, the more photo with the more different point of view you get, the more precise and well done the model will be. So you can obviously take from the same level when you are working around your section, but if you have the ability to take higher elevation photo using a UAV, it is even better.
There is another question from Tatiana that asks, can we use the same method for satellite images?
Well, actually, nothing prevents it to use it, except that with satellite, it is more complicated to take a lot of overlapping photos. And also the problem is that with a satellite, you will have only the same point of view, which is a top-down view from above, obviously. So in theory, it could be possible, but in practice, the stereo photogrammetry works better with the satellite imagery just because of the way the satellite imagery are taken from orbit.
And following this question, would it matter if there are several acquisition of the same zone but with different resolution? How could that be a helpful or a problem for those kind of digital models?
Well, actually, it can be both. It can be an advantage if you are able to take several sets of pictures with different conditions. Namely, for example, you are taking picture a day with a rainy weather and then another set with a sunny weather. Obviously, to add those images all together will provide you a better model because you will have more interesting photos. But it is also a very important issue, a technical issue. For the case of Curiosity, we have 3 different imagers that have 3 different optical parameters, different resolution, different focal length, and even worse, different colorization. You have seen that the navcam are taking photo in grayscale, whereas the mastcam are taking photo in full color. And sometimes, or more obviously, a lot of time, the software have a very hard time computing different sources. So if you have different set of images that is differing from an optical point of view, in grayscale from in one hand and in color in the other hand, it will be more difficult to merge those images. So my advice will be that you can obviously take several sets of pictures, but to the most as much as you can, taking them with a similar camera, which will make similar imagery.
Okay, thank you.
You're welcome.
Okay, I guess the last one, Tatiana say the maximum number of images for such technique.
Well, sky is the limit. It will depend on the power of your own computer. Obviously, a more powerful with a high-end CPU and GPU, a gaming-rated GPU will be better because the computer will be able to handle a greater set of images with greater resolution. But also, you have the time constraint. The bigger the set you are dealing with, the bigger the computation time will be. For example, in Kimberley, we had 2,000 images, and the model was computed across a week, literally a week.
Sorry, guys. The question was the minimum number of images.
Oh, the minimum. Sorry.
I'm sorry. That's my fault. Sorry.
No problem. Well, minimum is, it depends on the size of your object. For example, if I want to modelize my smartphone, I think that a minimum of 10 or 12 images from all around the phone will be sufficient. If you want to reconstruct a sedimentary section, which is 60 meters wide and 12 meters high, I think that a good minimum of images will be about 200. Yet again, it depends on the quality of your photo, and the best advice I can give you is to have the bigger overlap between photos and not to count the number of photos. Obviously, the bigger overlap you will have and the most point of view you will have, the bigger the dataset will be. It's always a balance on what you can take as a photo and what you can compute with your computer.
Okay, Gwenel, thank you very much. We must go ahead. Thank you very much for the good explanation. So, okay, we go back very rapidly to Cloud Compare. I will share my screen and we will try to load this new data set. So here I am. Okay. So, okay, I will just delete everything. You can even close Cloud Compare, start it again. And first of all, let's go in the data folder. Let me find, here it is. You see there is, by the way, also the mesh for the point clouds of the Blätterbach. If you want to explore a little bit what is in that mesh. We decided to put that mesh also because it's a nice way to have an idea how different a point cloud from textured mesh might be. So please don't do it. I will do it for you to open in a text file, but it might freeze your computer depending on the radar you are going to use. So you see that within such kind of file, you will find this list of vertices as we have been seeing before in the presentation. So you have the full list of vertices, and if you go down, 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 you start having the texture coordinates. So basically the UV coordinates we discussed before in the presentation that tell the 3D software you are using to visualize your data, how the data should be visualized, which part of the texture should be mapped on the 3D model. And of course, at the very end, you find the triangles. So each of these entry, this one, and this one basically describe one face of the triangle. I might be wrong, but I guess the other data, this information here is probably related with textures. I'm pretty sure they are. And but this gives you a good idea and understanding how the data is stored, and also it's normally stored in a similar way when you are working with when the data is loaded in memory. It depends by the software, but probably is in a similar way. Alongside the mesh, you also have two JPG files with that you can open them, and they look like something totally strange. It is the texture image that is used by the software then to, and it is stitched on top of the mesh data. But you would say that it doesn't mean anything looking at it like that. But of course, if you open the model, we can try it very briefly. If you open the model, what happens is that indeed you can find a very good resolution on top of your model, right? So, but you can play with this later probably if you want, and explore a little bit the data. So we can go ahead with the GeoCrater data set. So just in the parent folder, you can find a GeoCrater folder. So we prepared basically two data sets. I mean, they contain basically the same information, but this one with planes contain a little bit of extra information we will use just to skip some steps. So let's delete this mesh. I'm not interested in that anymore. And we can try to load this data set as a starting point. Okay, it took just a moment. We loaded the mesh. So first of all, have a look at the interface. You can have some information on the data you are working with. So in this case, it is a mesh. As you see here, there is this little, looks like a sea star or something like that. It's a symbol for the mesh. Just below it, it gives us an idea of the kind of information that are contained in this mesh. So for example, tell us that texture coordinates are present, so UV coordinates for mapping the mesh, and also materials definition, which are the ones that define which texture basically it's used on this mesh. Of course, something that might be interesting is, let's say, getting an understanding, because one of the problems you might find with this data set is that sometimes where there were not very good point of view, like in this case, you might find the colors are just blurred away, right? That is because there were not good information for the photogrammetric software to build up the model. So one problem I will say with this kind of methods is that you must be very aware of what you're doing, because of course sometimes the software will just reconstruct geometries by interpolating the geometries, the nearby geometries, but of course you must be aware that you might not even have data points there. So if you are going to use that 3D data set to extract, for example, all the planes like we are going to do, that might be a problem. I mean, you must be aware of that. Of course, we can change the properties of the mesh exactly like we did with the point cloud. So you have some preliminary information about the positioning in space. You can either enable or disable materials. Something that might be interesting is to have a look at the triangles, because of course you will see that there are points in this 3D model that have a lot of very dense triangles and others that have very big triangles. So that is an indication of the resolution you can expect to have in that location. Then of course, if a surface is perfectly flat, you can of course also represent a surface with a limited number of triangles, but we must be aware of that. Okay, so let's start with practicing interpreting this model. So as you see, as Barbara told us, we have possibly 3 different sets of fractures, like this ones. So just get your time to be able to navigate well the data. Of course, anytime you can recenter the rotation center for your view, you can use this tool here in the toolbar. At mine is at left, but maybe I just move it there. You can use pick rotation center, for example, like this one, and then click in a given position so that after the rotation will happen around that point. But even using auto rotational center is totally fine normally. So, okay, like Barbara said, we can use polylines to try to trace those fractures. Of course, we must pay maximum attention. So, for example, I see this fracture has a very good expression both in the top plane and in the front plane. So I can basically try to follow that one. To close the line, as in QGIS, just right click and then accept your newly created polyline. So you see now we have a polyline on top of the model. And if we were lucky enough to have a solid variation of the geometries behind that, the polyline should look something like that. Okay, but it doesn't mean much without the model. So we can go ahead and try to map different structures, different fractures. Let me see where I am here. Does look promising. Of course, always we need to pay attention to see whether the model has a good definition for what we want to map.
Sorry, where I have lost, where to create a new polyline?
There is a little tool here in the toolbar that is called Trace a Polyline by Point Picking.
Okay, thank you.
Let me try to trace one here. I'm not really sure I will be able to get a good data point here because the model is not so, has not such a good geometric resolution probably. Okay, so of course, if our point would be to estimate the orientation of those fractures, and we want to, let's say, we can assume those fractures are just plane in space. The next step will be to find the best fitting planes for our polylines. There is a dedicated tool here, which is under tools, under fit and plane, right? So you select a polyline, you can also select a point cloud and other kind of data, and you can find the best fitting plane. So I will try to zoom in on that plane, and you see we created the best fitting plane passing for that line, right? Of course, this has limitation because if, for example, the polyline will be taken, for example, on top here, where everything is flat, that will be very difficult. So my suggestion is to always look for geometries, planar geometries that you can trace at least on two faces of your object. So just look around, like for example, let's see this one. You can find it on this side face, but you can also follow it on the top face here. That might be a good one, right? Because you can see the fracture, the feeling of the fracture coming up on top and then curving in this direction. So that will be a very good example of a future we would like to map with polylines to extract data. How is it going? Everybody was able to fit at least a couple of lines?
Yes, it was.
Yeah, that's great. So I'm skipping forward a little bit because we are late. I want you to then experiment later if you are willing to. Sorry? And so that's fine. We have what I want to show you is that you can then export this data, but I will load the other. Let me do that. Yes, we will delete everything and then load again the other dataset, which is the one with planes, because Barbara did an incredible job in mapping all the little planes. So we can have a look at her result, which take just a moment. Let me see, memory, that's fine. Okay, so you see this is a more complex data set that contains a lot more information. You can try to open and close the various data. And in particular, we have already mapped a lot of planes. Like this one, that was probably the one I was mapping before. Like this one and many other different planes. So at this point, we will try to replicate the results Barbara got. But before that, I would like to ask Ricardo maybe if he could do a brief explanation of the stereo plot using the visual geology tool. Will you be willing? Oh, I can do that. No, Ricardo is not there. That's totally fine. So for the ones that of you that are not geologists, this is super brief and well, we cannot go much in deep with that. But a way geologists use to plot orientation of planes in space is called stereo plot. And to understand that, let's do like this. I will click here. That will create a line. So believe me, that line do actually represent a plane. And the point, this little point here, do represent the same plane. So you have two ways of representing an orientation of a plane in the stereo plot. The first one is by using one line. The second one is using just one point. And now, so you can believe me, we can have a look how they look like. So you might be able to understand. So this is a plane oriented in this way with an high angle in respect to the horizontal plane, which is represented by this external circle. And the normal to the plane, starting from the center of this circle, is then plotted, is then projected to the lower half sphere of this drawing. So basically, geologists can just look at this kind of drawing and understand, okay, this is in the intersection, this line represents the intersection of a plane with the half bottom of a sphere. So in 3D, again, looks like this. So the intersection of the plane with the half bottom of a sphere. And if you want to be more concise, you can just plot the pole of the plane. So the normal of the plane, basically, you just project the normal of the plane on the half of the sphere, and then you end up with of course, with something like this. And so now the problem is how we get this data from, let's say, from Cloud Compare to that software there. There is a nice plugin that makes much more than that, but we will use it just for exporting the data, which is called Compass plugin. And as you go under plugins, you can find Compass. You should have that. There are many. I would just like to say that there are many different plugins. Just have a look at the documentation online or try them out. You are not going to break anything, so just try them out. And the function we are interested in is the save function, or the export, interpretation, and measurements. So with this button, we can click and he will ask our name where to save our files. I will just use my planes. we don't need to select anything because this plugin will go through all the data available in this data set, and it will try to export that. So let's save it and look what happened. I saved them in my home folder. Here we are. So it created a file that is called myplane, that is normally a CSV file, a comma separated file. If you open it up in a standard text, you will find basically a table. We can also open it with Excel, for example. Okay, we need to set something here to be good to go. Let me just check. Oh, that's great. That's perfect. Okay. Okay, so in this file, there is basically a table. I will just remove this first column because we don't need, I mean, it's so long. And basically the information we are saved, or better, the information we're interested in are the strike and dip angles. So you know that a plane space, if you don't care about the location, is totally defined by just two angles of that plane. And these two data can be used to plot, actually, to create a stereo plot. So we will try to, let's say, delete all this information we don't care about, and we can try to save it so that my text file now looks more ordered, like so. If we go back on that page, I mean, if you just Google for stereo plot visible geology, you can find it. That will be one of the first entry in Google. So if we go here, we can see that we have a little panel we can populate. We can also import data using this little icon here. And we can provide a name, so Gale crater, change my keyboard, Gale crater. So we say that the data type is plain, and we must say which form. I mean, here you see that it should suggest the format to put your data in. So we just go here, copy all my data. We copy them here, and then the order should be dip to the right. So if we go back here, we see the dip angle is at the right. We can just accept it, and we can customize the visualization. So if we want to see the plane, the pole, etc., and then accept. Right. So we are actually looking just at the poles now. So just for you to understand, points in the center here, they represent, imagine they represent the normal to a plane that must be horizontal, right? Let me see if we can move it. No, I cannot move it anymore. That's not important. And we can see two different sets at both sides, basically, of this of the main, let's say, main fracture system that is basically horizontal. So basically, that is how you can go through your 3D model, map out information, derive something that is useful for you, and then use to produce actually some new plots, some new information that can be important for the interpretation. We need to go ahead. If you got question, please. We are here. We might spend 5 minutes for that. Let me know if any. So everything looks fine. We can try to go ahead. Are you ready? I know that that has been a little bit fast, but we should try to end before.
Yeah, yes, they have some problems sometimes with the program. I see.
Yeah, I am answering them individually.
Okay, perfect.
Oh, great, Ricardo. Thank you very much. Yeah, there might be troubles with your software. Just try to see whether different version you can find online might work. So for the next topic, we don't have much time, so I would like to ask Giacomo if he could introduce us the dataset we're going to use. Giacomo, are you there?
Yeah, I'm here. Yes.
Yeah, I will just stop sharing my screen so you can.
Okay. Oop. I will try to share my screen. Here it is. Can you all see this?
Yeah.
Yes,
okay.
Thank you.
So I will briefly introduce the main instruments that are orbiting Mars and that are capable of retrieving subsurfaces details. The two instruments are MARSIS and SHARAD. One is on board of Mars Express on an European Space Agency probe launched around 2003, and the others is SHARAD and is on board of Mars Reconnaissance Orbiter, orbiting Mars around 2006. The two instruments are quite similar because both are synthetic aperture radar that are emitting pulses of radio waves at a specific frequency and are capable of retrieving not only the first reflection of these radio waves at the top of the surface, but also on the subsurface. And depending on the frequencies that they emit, they're capable of reaching depths that are up to 5 kilometers for MARSIS and up to 1 kilometer more or less for SHARAD. But not only, the power to discriminate different layers are different. In fact, objects that are smaller than 70 meters are not detected properly by MARSIS instrument, while for SHARAD, the images, the data could, the resolution is around 20 meters more or less, and can reach up to 7 meters in specifically acquisition mode. But both of them are capable, as I mentioned before, to reach the subsurface. One of the main differences that you can see in this table is that the ground track or the footprint of these instruments are quite different. In this situation, we have MARSIS that is kind of 10 times bigger footprints than SHARAD, and also their relative resolution. So in just for a comparison, here are plotted some tracks that later will be used for by Luca for the practical activity. In green, you have SHARAD, and in red, you have the footprint of MARSIS. And as you can see, footprint of MARSIS can reach half of the planet, more or less. But there are tracks that are even longer. And going into an example of these radagrams, you can see on the left MARSIS and on the right SHARAD. And in this situation, we are in the North Pole, especially on ice cap in the North Pole. And on the right, you can see all the layers, the main layers of the ice cap. And while on the left, you can see half of the planet of the North Cap, and not only the layers. So having this different resolution, you can reach different targets. If you are more interested in the structure, geological structure and major features that are underlying the surface of Mars, you can maybe rely on MERSIS data, because you can reach up to 5 kilometers, losing some details, especially in the first 10 to 100 meters. While for Sharad, you cannot reach deeper levels, but you can describe with high details the first meters of the subsurface. So both of them are specifically born to investigate ice caps, both for South Pole and North Pole of Mars, but both of instruments are capable of discriminate layers underlying the subsurface, even in the whole planet. But it all depends on the target of your research. So for larger scale, Mars is quite better, but for details, Sharad is way more better. For example, one of the last papers released last year was the findings of Martian salty glacial lake underneath the surface of the South Polar caps, around at 1.5 kilometers depth, in an area that coverage more or less 20 square kilometers. So it could be really interesting to use both of them. And both of them are used also in three-dimensional environment, as Luca will show you later, but mostly for Sharad, because Mars is having tracks really large that can reach up to thousands of kilometers. It's difficult for the softwares to analyze such data of such dimension. In fact, most of the terrestrial software that we use are specifically created for terrestrial data, and terrestrial data is rare that they reach size length above hundreds of kilometers. So we need to tweak more the data to adapt them to the software, both open software and paid software. So this is almost all. It's just a quick introduction on that.
Giacomo, thank you very much. If there are questions for Giacomo,
yeah,
or we can just jump into the tutorial. I see no questions, so we can go ahead. Thank you very much, Giacomo.
You're welcome. I'm here anyway.
So, yes, I will share my screen again. So I would like to know if all of you are going to try to replicate this operation with OpenText. Well, it's a pretty large software to install, especially just for this exercise, but I would like just for you to have a feeling of some of the data we can use to create 3D surfaces. Anybody that really is going to try, or I will just, let's say, demonstrate that. Alessandro, Ilaria, great. So I will start my OpenText software. You should already have, let's say, an icon on your desktop or something else. And we will need to import data. Of course, the first time you start it, probably the dialog might not be exactly like this one, but there are no big troubles. Just go ahead with whatever the software is asking you. Let's have a look at the data set. And we prepared for you a very simple data set, which is this one, Sharad data set. If you open it up, you will see there is no need to unzip it, because it is already a project made exactly for this purpose. So if you are curious, you open it up, you will find a lot of different folders containing different data types, but there is no need to do that. And I would like to know if all of you are in this condition, because maybe just the main window open it up or if you are here, that will be perfect. Anybody? Ilaria, Adriano? Alessandro is here. That's great.
Sorry, how did you make to show Marcy's new test and all that things? Because I was away for 2 minutes and I lost it. So
yeah, and okay. I mean, this window here, I just open OpenText. And the first thing OpenText will ask me is the survey I want to work with. So just open OpenText. If you have a different screen, because maybe you jumped in a project, no, it is not Cloud Compare, it is OpenText. You can have a look at the software page on the, yes, thank you, Ricardo, on the website. It is listed that, oh, I'm sorry guys, you can find the list of the software there. And great, thank you, Ricardo, for replying to the chat messages. The first thing we want to do is import the data. And the way OpenText works is meant to be used with seismic data. So seismic data are normally distributed as seismic volumes, and which are, let's say, we can simplify, it's like cubes with voxel containing seismic properties, basically. But we can also adapt the software, or better, we can adapt the data coming from Charade to be operated within the software. So the first thing is that we need to import the dataset, and we will use this function, extract survey from zip archive. It will ask us to select basically this data file. So I really need to go and look for the data. Let me see if I can find it. Data, that's under plan map. Sorry, guys. Winter School, day 5. 3D. No, not that one. That's 8. Data, 3D modeling, and here we are, Charade data. We can open it, and as you see, we'll add a new entry in the survey route folder here, Charade Polar Cap. Of course, there are many properties connected with the definition of the survey, like the ranges, but I mean, they do not completely make sense if you are not working with volumes. So just leave those parameters like they are. And then we can select the project, right? And something like this should show up for you. Ilaria, my shared data file show only a Polar Cap file. So you mean you don't have a Charade data? Charade data. By the way, because Nicole was a student that she worked with us and made this data set available. So that's why it's called Nicole. And we uploaded this package again, maybe. So you don't have Charade data.zip, Ilaria. Try to download. Okay, thank you. Let's try to have a look on the cloud whether you can find this data set. Should be there, but I probably can also share it over the chat. It's not that big. Maybe Ricardo can. Thank you, Ricardo. So as soon as is there anybody that is at this point now?
I am there, but I also have a lot of labels like numbers with time, cross lines. So maybe I forgot to toggle something off.
Yeah, probably it's just a visualization option. That's no problem at all. Also, like in Cloud Compare, you can move everything around, but as soon Yes, there are many people that already have this view. So to work with this software, the first thing you need to understand is that there are two modes in which in every moment the software is in. One is the navigation mode, I would say, and the other one is the tool operation mode. To alternate between the modes, you can either press S key on your keyboard, and that will alternate between the modes, or you can use this switch to view mode, right, in the toolbar. There's switch to view mode, that then you click, and then it becomes switch to interact mode. So view mode, interact mode. Interact mode is used for using the tools you will be using, and view and the interact mode. No, the view mode. Sorry, guys. And the view mode is used to operate on the 3D scene. So if I'm in the view mode, I can rotate just by left clicking this region. I can rotate it around. If I give it a push, it will stay rotating forever. And if I switch off the mode by pressing S, I will not be able to move it anymore, right? Because that is how it is intended, the software. So just switch back and forth. Just switch back and forth, and you can either move your cube, or that is basically your survey, or you can operate with the tools we will see later. So just keep that in mind, because maybe you click on that and then you forget, and then you don't know how to go back. Just press ask. That will alternate. So the way the software works is that you have several kind of data types you can use. Those data types are predetermined. So you have, for example, in this scene, this set of data types you can use, visualize, and explore. In our case, the type of data we have are 2D lines. So as you see now, there are no data loaded. So the first thing we want is to let the software know we want to load some data. So I just left click on 2D lines here, right? So left click 2D lines, and will give me several data sets I can load. I will just select all of them. You can also say what happens on OK. So display projection line only. That is totally fine. I press OK. And now what we see are the imported lines on the surface for the radiograms. Okay, just something I wanted to mention is that radiograms, the vertical dimension of radiograms is time, right? They are not being converted to depth, but of course the time it was taken by the radar signal to propagate in the heights is proportional to the depth. So just keep in mind, if you want to take a measure about the thickness of something, you are not measuring depth. You will be measuring time, but in this case, just to make this section fit in the software so well, the time also is not something you can read as a scientific value. So if most of you are at this point, we can try to go ahead and actually visualize data. To do so, you can right click here, select attribute. So I'm on 2D line. I have my 6 different 2D lines, and you see here the software will suggest you what to do. So right click, select attribute, store 2D data. So basically for each of these 2D line, we can have multiple attributes that are associated to the same data. Like we saw before, for example, with the point clouds, right? For each point, you can have the color information, you can have the intensity information, you can have the density information. And especially in seismic software, seismic data processing, there are a lot of different information that can be derived from seismic data and might be helpful to you for the interpretation. Of course, now we are not working with seismic data, keep that in mind, but they are quite similar in terms of a kind of software we can use to show them. So I will just load one of the section, and this is what should happen on your computer. Is it working for anybody? Yes, great, thank you. So we can display also all of the section. If I remember well, we can say display all, no, cannot remember, display attribute, right? So if you right click on 2D line, you can find display.
You can repeat the last step again, maybe load another section.
Yeah, sure, that's great. So we loaded this section. Now we can see it here. We want to load another one. So I just go on the one I want to load, and below it there is right click. You see it? So if I do right click, it gives me the opportunity to choose which attribute I want to display in my view. So select attribute, store 2D data, charade, and the software will load another section. So we can also load all of them at once. We just right click on 2D line and then display attribute, and we select charade. And nothing happened. Why? Display attribute charade. Well, we can still load like this. That will be not a big problem. So load all of them. And here we are. So of course, in this case, this is just a small portion of the polar caps, but you see that mostly the different section, they tend to match quite well. But if you were going to make some detailed interpretation, of course, some further processing will be needed to make them match perfectly, because of course, the data you can download from the data repository for charade are quite, of course, good, but if you try to use the information, the geometric navigation data that come from together with the data to put them in 3D, you see that you end up with some little troubles here and there, and there might be a way to improve that. And of course, if you wanted to do detailed analysis, you will need to do that. Lithology composition due to red, yellow, blue reflection. Well, so the way the radar works is that it pulses a radar pulse, basically. And then every time the pulse, it's not different how it works in seismic, but with a different principle. No, but basically the same principle, but with a different kind of wave. So the electromagnetic wave travels through the ice, and whenever it finds a contrast, so a sharp difference in the dielectric constant, so the velocity of the wave in the medium, it will produce basically a reflection. So what we are seeing here in red are strong back reflected radar signal. But I must say you that I'm not an expert on radar, but should be something like that. So ideally the idea on how it works should work like that. And this is ice. It is basically ice, and the reflectors are really are basically dust. So when the pole was forming, there has been a layering in between ice and dust, ice and dust, ice and dust. And what we can see now is very likely that the red, sharp red horizon are just dusty horizon. Okay, so you can navigate your data. We have 20 minutes. We should be able to do something great. And of course, you can change a lot of different properties. So for example, you can change the color bars you want to use. So you can change just for one. You can also change for all of them. If I'm not wrong, there is something here, color setting for charade, and you can choose different color bars. So you can try to do so. Let's find out a nice one. Let's try with this one. That was the default, looks nice. Okay, so what we were saying before, these data are images basically. So they are not really 3D, but if you use the information you have from the navigation, you can try to put them into the 3D context, which is very nice because it will allow us to try to perform a little bit of an interpretation. Of course, you can visualize the section in different ways. Let me see if I remember how we can. Another interesting thing is the Z scale here. So you might be willing to change the Z scaling here. You look only one section in a plane, not in a 3D cube. Yes, there is a way to do so. I was going to tell that if I remember where to open the dialog. Display, not here. I basically forgot how to open it. Here we are. So under the property of the given section, you see under 2D lines, you have all the sections with different name as numbers, y. And if I click on charade, which is the property we are looking at, you can right click, and under display, you have different possibility for displaying that data. And you can also open the 2D viewer, right? So this is a way to look at the section in 2D and possibly performing your interpretation here. You see basically that you have similar elements which are very similar to the ones we have in the main window, but there are several options. So there are less options because of course in 2D we can only have 2D stuff, right? But I want to work just in 3D. You can of course work going back and forth from 2D, 3D. That might be very useful. But for the scope and the time frame we have now, we'll just jump to the interpretation of the layering, and we will see a nice tool. So how to trace your interpretation using the tools provided by this software. So we go under 2D horizon. And if you click on that, it gives you different possibilities. So add is not to add new, but it's add from the disk, basically. So you must have already traced that and saved that. Track new is what we are looking for. If we enable it, you will see a window load up, and you have several options here. Which I must say I'm not so good at understanding because they are made for seismic data. So of course, that will be better to use this software with that. So it will be more easy to understand what they do. And what we want to do now is trace any given horizon we are interested in. You will see that the software is able to do the auto tracking as you see here. That is really cool. So for example, if the first layer I want to trace is the top one, that is the first reflection, it's not really a layer, but it will be the surface. You can zoom in, and of course you can switch between visualization mode anytime using this button, right? So you can switch between handling your model, so changing the orientation. Then I press ESC and I'm back with the arrow. So let's say if I want to try to trace this horizon, I just click and drag. As soon as I stop, the software will do some computation and will try to auto optimize the track, right? At this point, I press ESC, so I change mode. I can rotate my my 3D model. And for example, I want to go to trace the same horizon in a different place. I press ESC again. Okay, and so I get this little square. The vertical scales of those sections are basically time. That's not space, it's time. But due to the processing, please don't believe the vertical scale. You can find depth conversions. Yes, but of course you need to know the properties of the material. So one way to do that will be to let's say, create your 3D geological model, so you can attribute possibly different velocities for the different properties, and then use that information to correct that. But I'm not sure if it would be so easy to do that in this software here, because it's not really done for this, for doing this. So we go ahead, we trace our horizon. I will be not so precise. So for example, this one, you can go back and forth from the two modes this software works with. Okay. Change my view. We can move around. Okay, so basically in just some minutes, we did the interpretation for all this side. We can go on the other one just to have a look. And we can start to do the same. Of course, you can enable, disable each radiogram if you need to be more precise. But as you see, that is very easy to do. I just switch back and forth from the two modes, from editing mode and interaction mode. Okay, so this is a nice surface. We still have to do the interpretation in the inside, so I will try to look for which section I really want to disable to do that. Not that one, maybe that one. Yes, that would be good. So you see, is if I disable the section, you still end up having these zigzag lines, which represent the horizon we are tracking. We are currently tracking. So we can just go again and select the new 3D horizon one, the one we just created, and we go ahead. Is it working for everybody? That would be nice. Cool, nice. Of course, I mean, this is not a software I would like to suggest you to, I mean, if you are working with this kind of data or similar data, of course, you could be using this, this tool. But I mean, it's basically dedicated to the oil industries, more or less. And it is used to do the seismic interpretation of the data. Of course, you can do that also for scientific purposes, not just for the oil. Okay, let's say we are happy with that. Then you can try to improve a little bit, but I just want to show you the last thing. That is how to generate an interpolated surface. When a red line separated by a blue patch, a red line separated by a blue patch. Okay, so there are kind of interruption, right? So here is the key. I mean, as we did every time in those days, there is a kind of interpretation going on here. We don't have the time to do that in detail, but you know, we must try to understand why there is a blue patch in between the red lines, of course, and whether it might be a discontinuity, like some kind of fault or fracture. And if that is our interpretation, we might want to model also that future as a different surface and so on. So you can, for example, if you were tracing this horizon, it makes sense that you just connect this horizon with this one. But I was saying that this software is not really the best one to do geological modeling, but it was just the only one that you could download for free. So I must say that they are great because they are leaving the software for everybody for free. What you would pay are the plugins. So, but it's still cool to be able to do this thing with this program. So the next step I would like to show you in this program is the clutter from topography remover. No, it's not possible to remove the clutter with this software, of course, because you need to simulate the effect of the clutters using an DM and stuff like that. As far as I know, because maybe I'm not so updated, it's very likely that you will need dedicated pipelines. Okay, so let's say we are happy with this horizon. Let's say we want to make another one. And for example, we go again under 2D horizon, track new, and we have another one. So we can also rename them with meaningful name if we want, and so on. And for example, I can trace this one as a second, and I can work my way again. I can work my way. Okay, very badly traced. But so basically we can trace any number. Let's say it's this one we wanted. Any number of horizons. Okay, just 10 minutes, so we are very good with the timing. That is nice. And the next step is generate surfaces, right? So we have seen that basically what
before
yes.
generating surfaces would be good to show how to remove points, because there are a few questions about that. Okay. It's not the way it works is that basically you can have only one horizon per section. So let's say I'm working on this horizon here, and I do something wrong in this position. I will just need to trace it again. You see, I trace it again, the wrong points got removed, and I can trace another segment. If I say I want to remove all those points, you don't really need to go in and delete one by one, because maybe you followed the wrong horizon. Maybe it was this one that you wanted to follow. So you can just trace here again below. And the software will say, look, I can only have one horizon within this 2D horizon on that section, and we relocate the points in the right place. That's the best way I know. Probably there is a way to select point by point, but I'm not sure. I just wanted to show you that if you open your section up in the 2D display like this, 2D view, you can do the same work here basically in 2D, so you can be more precise. So for example, I want to go ahead and trace this horizon here. I can just work my way here, right?
So probably I did something very bad here, but I can change it again. Okay. Okay, we can close this window, go back in the 3D, and we can try to generate some surfaces. We will have to try a little bit with the parameters for the interpolator, because of course it depends how many points, how good they are. But we can choose one of the two horizons we traced, and please don't do like what I just did. See if I can fix that. Yeah, but that's not so important for the demonstration. So what we can do now is right click on the 3D horizon we want to process. And under workflows, there is the right 3D horizon. And you have several options
Lucas,
here.
can you show again how to go back from 2D view to 3D view?
Yeah, you just close the window. The 2D windows, you can close it, and you will not close the 3D one. So for example,
to go to 2D view, I think you have to go to display. Yeah.
Okay, to go to 2D. Okay, right click on the properties you want to display 2D viewer, right? Mine is there. That's a totally separated windows. You can zoom in, out, and see the same 2D objects for this special section, only for this section, actually. There are other kind of types you can use, point sets, fault stick sets, which are used to model faults, basically. Are we okay with that? Okay, so to create a surface, right click on the 2D horizon, workflows, derive 3D horizon. There are several methods. I will try with triangulation. You can experiment, of course. And let me see what happens. Sometimes very strange stuff happens. Sometimes it works. This time didn't why. Let's try with this. No, I'm sorry, guys. So basically it created an horizon, and you can find it under 3D horizon. Just experiment with different types of interpolation. Probably this software is not the best one to do the modeling, actually, to do 3D modeling, but gives you a very good idea on how you will be working. You can add a 3D horizon here, and that's the new horizon we got, right? So let's see, basically it interpolated the points to create a planar surface, right? It tries to match all the points we got. And of course, you can do the same work for as many horizon you might want. And to create faults, just a little very fast explanation. Instead of creating 2D horizon, you would create a fault stick set. So if I add a new one, I can basically trace on the section a set of sticks like this one, which is basically like tracing the horizon, but tracing faults basically. And you repeat this work on many different radiograms or many different seismic sections, whatever you're working with. And then at the end, you can generate, by using this toolbar here at the bottom, you can generate the 3D surface corresponding to the faults. So as I said, this is not really a three-dimensional geological modeling software. Look for, there are many commercial. 3D Move is one. There is GoCAD, there is 3D GeoModeler, Leapfrog 3D, and those are really specialized in creating this kind of geometries. But I believe this is a very nice way to get into it, because it's a software you can use basically for free.